Hi everyone. So today we're going to look at acidic salt and trying to predict its behavior as well as how to calculate its pH. So when we're talking about salts of strong acids and weak bases such as the ones that are listed here, they basically form acidic solutions. Now if we want to understand the process as to why this is the case, we can take a look at a good example which uses HCl, a strong acid, and ammonia, which is a weak base, to form ammonium chloride salt. So when we look at this salt as a formation and we see how it works in an aqueous solution, we can kind of predict its behavior as being an acidic solution. The reason for that is that when we have this salt dissolving in water, we're going to have two different ions that are forming. The anion, which is the chloride ion, is a weak conjugate base, which means that basically it is a conjugate base to HCl, which is a strong acid. So when it reacts with water, it's not going to have any effect. So there's not going to be any reaction that occurs. But when we're looking at the cation, which is the NH4 plus, it is considered a strong acid because its conjugate base, which is ammonia, is a weak base. So when this strong acid, if it starts to dissolve in water, we're going to see it react with that water and it's going to basically hydrolyze the water. So what ends up happening is that proton that's in the ammonium ion is going to transfer over to the water and it's going to end up producing ammonia and hydronium ions. Now, because this part of the salt had no effect, but this part of the salt did, and it produces hydronium ions, we know that hydronium ions will make the solution acidic. So then the solution for this salt is based off of the ammonium ion, and we know that the solution is going to be acidic. So that can bring us to practice question 1. Practice question 1 is asking us to calculate the pH of 0.10 molarity of ammonium chloride salt. So when we're looking at this again, we're talking about the fact that this salt is produced from a strong acid, HCl, and a weak base, ammonia, and that will result in acidic solution, an acidic salt solution. So we already established that the chloride ions are basically considered spectator ions because they're a weak conjugate base and they have no effect on water, so it's not going to produce any kind of ions in the solution, so it's going to remain neutral. Whereas if we're focusing on the NH4, its ions are a relatively strong conjugate acid, so it's going to hydrolyze with water, and when it hydrolyzes with water, it's going to produce hydronium ions. So that is what is going to affect our solution and making it acidic. So now if we were going to create a reaction based off of this, I would say NH4 aqueous plus H2O liquid reacts with NH3 aqueous plus H3O plus, which is also aqueous. And we know that this is the reaction that is driving the behavior of my solution. So I can create a rice table for this. And I know that looking at the molar ratios of each item, I have a 1:1:1 ratio. And if I'm looking at the initial concentrations, I was told that my salt solution, or my salt had 0.10 moles. And we know that although this is the initial concentration of my ammonium ions, I still haven't formed ammonia or hydronium yet, so this is going to be 0. And then when I'm looking at the change of my concentration, I know that there's a specific amount that this concentration changed by, and we're going to denote that with minus x because it's going to decrease. And that same amount that decreased the initial concentration is going to increase my ammonium and my hydronium. So I'm going to use plus x and plus x. And then when I'm talking about my equilibrium concentration, I'm looking at the difference between my initial minus the change. So it's going to be 0.10 minus x, and then just x and x. Now, it's important to note, though, that because we're dealing with a conjugate acid-base pair, the conjugate acid being my NH4 plus and my base being NH3, we know that this acid-base basically differs by 1 proton. There's exactly 1 proton transfer from this conjugate acid to this conjugate base. And because of this, we can skip the whole Rice table because we know that that is going to mean that there's a negligible amount of my negative X. Okay, and so now we can just then use the values and sub them into the ionization constant of my acid and then solve from there. So as I was saying, because of this reaction being the driving force to produce an acidic solution, we know that the constant that we're going to use is Ka, and the Ka is for my NH4 plus because it's acidic, and we know that it is known as the conjugate acid of NH3, right? And my NH3 is my base. And then I'm going to use Kw to calculate my Ka. Now it's important to note the values of my ionization constant of water. So my Kw is always 1.0 times 10 to the power of negative 14. And then when I'm going and looking at my table for the ionization constant of my base, and my base, as I mentioned, is NH3, I know that that is 1.8 times 10 to the power of negative 5. Okay, so I'm going to use these values to calculate my Ka. My Ka is based off of my ionization of water and my ionization of the base, and I'm going to take these values and sub it in. So I'm going to get 1 times 10 to the power of negative 14 and 1.8 times 10 to the power of negative 5. And when I put that into my calculator, I'm going to get 5.5 times 10 to the power of negative 10. Now I know I can also calculate my ionization constant of my acid by taking the concentration of my products, which is NH3 and H3O plus, over the concentration of my products, which is NH4 plus. And it's important to know that you don't need to use the ice table to determine this because we know that it's a 1-to-1 transfer of protons. So I can simply just say X times X over 0.1 minus X. And we know that this is going to equal 5.5 times 10 to the power of negative 10. Now, we want to know if we can just use a simplification to solve for this instead of using the quadratic formula, and that simplification is based off of the 500 rule. Okay, so by looking at the 500 rule, we are looking to see if the concentration of our acid initially over the ionization constant of our acid is greater than 500. And so we can take a look by actually plugging this in. So we know that the concentration of my acid initially was 0.1, and I know that the ionization constant of my acid is 5.5 times 10 to the power of negative 10. So I'm going to solve for that, and I get 1.8 times 10 to the power of 8. And we know that this value is actually much greater than 500. So we can then just say that we can ignore the negative X in the denominator and just assume that the concentration of NH4 plus is just 0.1. Okay, so then that means we can end up solving for our Ka as x squared over 0.1. And we know that this is equal to 5.5 times 10 to the power of negative 10. So if I want to solve for x, I'm going to times this by 0.10. I'm going to square root this both sides, and I'm going to end up with x equals 7.454 times 10 to the power of negative 6 molarity. We also know that this value is in fact our hydronium ion concentration. And so because we know that that's our hydronium ion concentration, we can also find the pH of our solution, because our pH of the solution is based on this production of hydronium ions. So I'm going to go ahead and I'm going to find the negative log of my hydronium ion concentration, which is negative log times 7.454 times 10 to the power of negative 6. And when I plug that into my calculator, I'm going to get about 5.13. So then what this means is that my salt solution of NH4Cl is in fact acidic because it's going to produce hydronium ions. When I calculate using the ionization constant of my acid, when I'm trying to calculate that, I end up getting the concentration of my hydronium ions, and I use that to tell me my pH, and I know that the pH of this salt solution is 5.13, which is acidic. Okay, and so that is how you find the pH of an acidic salt solution.